All right, thanks you guys for showing up. This is going to be a talk about glass working from a do-it-yourself perspective. I'm Tomak. I've been doing this for a good chunk of my life at this point. For the things that we're going to talk about, starting with colors, and then with the glass chemistry, and then equipment, and then neat things people have done, suppliers, and where to go to learn stuff. No warranty or copyright or liability is implied in all this. It's a little dangerous, and I'll get into some of those dangers at the very end as a kind of an afterthought. So colors in glass are not like colors in painting. Who here has done glass work before? Anybody? A couple of people. This is good. Colors are unfriendly, they're intolerant, they don't mix well, they create stresses in the glass. With paint, you can mix any two colors. You can mix two greens to get a shade of green in the middle. You can mix two greens of glass and get a pukey brown or something bizarre instead, or have some crack on it if you don't know. The colors come from metal pigments primarily. The blues are about the easiest to do. Cobalt, as you probably know, is that. And cobalt, if you buy it in bulk, is like 50 bucks a pound. If you want to do large quantities of glass color, you're better off making your own. If you're doing small projects, definitely buy. You can go to Gaffer, Reichenbach, or elsewhere and pick up like small bits of each. But if you're insanely ambitious and you need like 200 kilograms of a color, definitely buy the pigments. We'll get into where you can buy those things from as well. Greens, you're going to use chromium mostly. Greens and yellows are a big incompatibility. This is a sheet of stained glass I had done, and to get that green-yellow mix, I'm actually doing casing. I'm putting a layer of clear glass as a barrier between the green and the red, because the chromium will interact very negatively and create one of those dark, opaque browns that you don't want to see. The yellows are harder to do. It's cadmium and selenium for the reds and yellows. I don't do that myself because when you add cadmium and selenium to your glass batch, it will evolve, it'll boil off up to 90% into the air. So you'll be sucking more of the cadmium than actually putting in color into the glass, and it just sucks. Back in the day, they used to like mix the glass batch with the cadmium and put it in sealed clay jars and put that in the furnace and cook it for a long time until it gets in there, and that's a good way to seal it together. Purples, manganese is a good, easy, cheap way to do that. The nicer purples are done with gold, ruby, and some other additives. The way you prepare the stuff is a bitch as well. The cobalt is super easy. The yellows are not. The purples are not. Even the cheap manganese, it's like you can't bring it over 1200 Fahrenheit, or you'll change the valency of the manganese and get sort of a clearish color from a nice purple color. This is a sample of blue where I've mixed a silver cobalt blue with a copper cobalt blue, and then I'm putting it in a reducing atmosphere, and that brings out right on the surface, the silver will come out of solution and form that beautiful mirrory surface where the cobalt doesn't do that. So you can intermix colors that look the same to get extremely different results. This is a sample of how the glass colors can be incompatible with the other glass, the base clear glass. In this case, this is double checking Reichenbach yellows against System 96 glass, where definitely number 18 is not compatible, even though it is sold as such. Those colors are pretty finicky, and the way those yellows are prepared, you're getting a colloid that comes out of the clear glass and forms these microscopic particles of yellow and orange in this case, and if you hold it at high temperature too long, these particles get larger and larger, you get a little more opaque, and it'll strike out, it'll turn dark brown. If you've overdone it with a large batch of the yellows or the reds or the gold rubies, you haven't really destroyed it, you just bring it back up to really hot 1400, 1500 Fahrenheit, and you'll redissolve it, and then as you cool it, you can re-achieve your yellow and other colloid-based colors. This is a blurry picture of System 96 nuggets, premium nuggets from Olympic, where I'm measuring out a quantity of chromium, 3 parts chromium to 1 part iron, 1 part copper. That gives me a very nice green. So to do that, I'm shoveling it into the furnace, mixing into each batch like this and cooking it for about 4 hours at high temperature, and I'll go in with and manually stir it. You can use the technique where they add a pumpkin or an apple into the mix, and that'll create gaseous churning of the batch, which is a fine way to do it too. But some of those pigments are really stubborn, and it takes a little extra heat, extra manual stirring to really get them into solution. Once they're in solution, they'll stay that way. So, you know, if I have a lot of scrap glass that colored green colored, I can throw back in later, and I won't have to bake another 4 hours. It's pretty easy that way. Here's a sample of white that I've been doing. There are a couple different ways to do whites and a couple ways to do opals. Opals is that quality, that whole spectrum of glass that's not transparent. Some people need that for different applications. This one is a fluorine-based white, and most of the other whites you see are phosphate-based, where you'll add some phosphate to the glass. Bone ash is a common source of that, and Runyon suppliers, ceramic suppliers will have that stuff. The fluorine, it creates a stronger, more opaque white, but it's not good to use. You can burn out your lungs with fluorine gas. It also is terrible eating away at the insides of your furnace when you're using that too, because it'll etch everything. Phosphates are a little friendlier, but they don't create as strong of a color. If you want to do like a translucent white or translucent white mixed with other colors, you'll definitely want to go with that chemistry instead of the fluorine. This is from Glass Art Society. Somebody's giving a beautiful lecture, and Corning and other places will have this. Is a very simple illustration of the basic colors you can achieve, and valencies that will change those colors. Getting the different valencies you can either control by giving a reducing or oxidizing atmosphere in your furnace, but as you add different metals in combination, it becomes extremely complicated. And even arguing with manufacturers about the activities of those metals, they always end up saying, well, you just better test that yourself. Thank you for your expertise. This is a fun one. These are some of the more exotic colorants you can use in your glass if you can get a hold of them. I did pick up from Gaffer some neodymium, which is not too expensive. It is a simple dichroic where it will change between a blue and a purple depending on the light. You can like have it under indoor fluorescent lighting, which is a very different spectrum from daylight, and it'll look one color, and you walk outside from the same angle as a completely different color. It's pretty spiffy that way. Another one of the higher periodic table metals you can use is uranium. You can still buy uranium glass. You can go to the DIA, and it has some beautiful kind of a yellow-green bases. This is that same yellow-green color. I haven't died of radiation myself yet. I would not take this to an airplane. TSA would freak out, call me a terrorist, and take me to Guantanamo forever. Gaffer sells it still, and they manufacture that in Australia. They mine a lot of it.
Fluoresces beautifully.
So sometimes, if I want to learn about a glass color and mimic it myself, I have to determine what's in it. And a little X-ray spectrography is very handy for that application. In this case, Zimmermann glass went out of business some years ago, and I had some samples. I wanted to know how they make this gorgeous silvery reducing green. So I had an analysis done by a friend, and I got these results. So we've got our chromium in there, which is a predictable ingredient, silver, Ag right here. Certainly that will account for some of that silver, but it turned out this gold yellowish color. And it's very instructive that there's some barium and germanium in there. I tried it myself, and I didn't get the same results. I would have to do a long series to check the reducing atmosphere and other aspects of it. This is not surprising because even the period recipes, when you go to like reproduce some of them from 100, 200 years ago, unless you know exactly how they were mixing those pigments in and preparing the glass, it's a crapshoot whether or not they get the same results. This way. So we're going to move on to the base glass. Glass you can buy in cullets. You can get some batch, spruce pine batch. is probably half the cost. If you're buying just nuggets of clear glass for your project, it's about $1 a pound, up to $1.50 for some suppliers. Leaded glass is another option. They love that in Czechoslovakia and Austria, where they do huge amounts of casting. Swarovski loves the leaded glass as well. It has a little different refractive quality, but it's also softer. And when you see lead crystal, one of the reasons that it looks like it does is the density of the glass from that lead gives it a higher refractive index, so it'll split up the light a little bit more, give you a little more rainbow effect. But also it polishes faster, and that's half the reason they love it. In much less time, you can get that perfect faceted surface that you want on those Swarovski crystals. For regular glass, it comes in two basic varieties. The bongs you see and little wrist beads and so forth, that's all borosilicate, flamework glass. It's different from soda lime glass because of the boron. Boron actually has this weird property where it shrinks slightly, so if you start with pure sand and add a little bit of the flux and some boron, it won't crack immediately when you take it off of the fire. So for smaller articles, you can just melt one spot, pull it right into the fire, and it's not going to crack. Most glass is not friendly that way. You heat it up to working temperature, you have to anneal it for a long time to bring it down to room temperature very slowly. It's a temperature differential between one side of the piece of glass and the other. It'll just crack, especially through the strain phase around 800 to 1000 Fahrenheit. It has to be less than 3 degrees difference between the center and the outside, or it'll crack on you. And below that strain phase, it'll crack if you cool it too fast, but above the strain phase, it'll start incorporating stresses, and it might look okay afterward, and then a year later you go to wash your cup or your plate and it'll crack on you there because it didn't properly get annealed through that higher temperature range. What we got here is all the ingredients. You've got sand on the top far left, and then soda ash. You can add some potash, some calcium carbonate is whiting, which is another primary flux. And you can control the coefficient of expansion depending on which ingredients you'll add. System 96 is very popular. 90 is another one, and you can actually take one in a big molten batch and add a little extra of this and that to change it over to the other one. The expansion coefficients, English and Turner values, are like 100-some years old, where each of these ingredients has a different value. So this silicon is fairly low, the lowest of them. Sodium is the highest of them. It's like 4 times, or a little more than 4 times the silicone. So how much sodium you add is going to make it a more expansive glass. And if you want to change over from 96 to 90, you're going to want less expansion. So you're pulling out some sodium, putting in a little more calcium, or just leaving sand. You've got some latitude there. So this kind of calculation process is very handy. I only learned a few years ago that it's already out there in Excel spreadsheets. Getting them from the manufacturers is next to impossible because they're very secretive about their processes. And you have to dig through archival research from way back and then kind of map forward with new technology that's available to engineer how to do some of that stuff. But I had good results with this, so I'm pretty proud of that. I even took some sand, not granular sand, but pre-crushed flint, it's called, which is a powdered form of sand, plus all these other ingredients, and batched out just to prove that I can get consistent, repeatable results between purchased cullet or between batch from spruce pine or Lubino and between completely homemade glass. Sometimes, if you're doing a large batch of some of the colors, it's cheaper to start with this stuff, especially for the phosphates. The chemistry is so different. You're not going to be able to start with nuggets and then add that much bone ash and other compensating ingredients to get usable matching coefficient of expansion colors. So going on, once you've got some glass, there are a lot of things you can do with it. You can do what the glass blowers do. You put your punty or your blowpipe in there and you'll make some nice stuff. Just a proof of concept, simple glass vase. And these have been in production for 100 years as the studio art glass movement, where people are making it in their backyard. They'll make a day tank and they'll blow their own glass and put it in an annealer, purchased or homemade. It's it's got innumerable varieties. Everybody out there is looking for new ways to produce the thing, get some really distinctive style going, put it in some galleries and so forth. But there hasn't been a lot of breakthroughs in the last 100 years. You've got dichroic, which is a very nice thing that we'll talk about shortly. But stained glass is another aspect that hasn't seen a lot of innovations. I got to visit some of the shops, and they do a very efficient job. They have a few novel, but nothing really pioneering breakthroughs. And I wanted to do some things like this, and I got some nice results. But I've learned the hard way that if it costs 10 times as much for me to make a novel piece of stained glass, the people who are making windows are not going to buy that. It's just out of their price range. But it was fun to do some of that. Here's a sample where I've got some specialty mixtures. I'm not sure you can see. There's a lot of contoured surface on this too. A lot of colors churned together in some novel ways. I also took some, cracked it apart afterward, refused it together with some additives in there to make simulated lapis lazuli, or this kind of volcanic surface. I'm hoping there's.
Oh, yeah.
There you go. It was a lot of fun doing this, and we'll get into some of the things because this was not an end product for me. This was a means to do some sculptural, three-dimensional projects that we'll get into. But this is some stainless steel rollers for making my own stained glass. I got to put a lot of pressure on that. Doesn't have to be very hot. These rollers, you want them about room temperature. You can go off a little bit, but you do not want them hot because hot metal will stick to the hot glass, and then it'll wrap around the rollers. Oh man, have I done that a couple of times. That's why I've got this massive, 8-inch cross-section steel tube going, because anything less, it'll just pull that steel apart. It'll bend the axles. I've mangled gears and everything else, learning how to do stained glass sheet this way. Often you'll have it kind of a moving tray off of the backside that will catch the thin glass without, because if you just like dump it out the backside, it's like, you've just spun a pizza bread dough. You can't just push it, it'll just wrinkle up. So you've got to carefully draw it out this way and that way. It's the same thing with the glass. And these rollers will chill the surface sometimes a little too much. You get little micro fractures in the surface, and then you'll want to put it through this big flash oven where you just slide it under, preheat it, and just nuke the top to liquefy the top layer without liquefying the whole thing. And then you can put it in your layer. A layer we'll get into is a continuous angular. This is, forget if this is Ouroboros or Kokomo, one of those production professionals. They've got, you're looking at the background, you've got two of the tanks where they've got color. And in the foreground, we've got the rollers that I just showed you, only theirs are bigger. They've got probably a 14-inch diameter rollers there. And then you've got this guy, he's holding some sticks in his hand. So the guy on the left of the red one, he's got scoops. And there's actually a couple of people there who will bring out scoops of molten glass of different colors, and they'll dump them on the table, and the guy with the sticks, he'll just kind of mix them this way and that, and then he shoves it into the mixer, and it comes to the backside, and that's how you're getting the conventional Tiffany swirly colored glass. It's a pretty neat process. It's very important that those glasses have the same expansion coefficient, or all that glass is going to be scrapped. And in fact, these professionals, they scrap 30% of what they make. I learned that while doing this. It was impressive that even after all this time, 30%. And they've got some nice polarized screens and check for stresses. What's that?
They reuse it then.
Well, they say they reuse it, and technically that's true, but you can't put it back into the pot.
No.
Because now you've got a muddy color that you're starting with. You have to start with a pure color. So by reuse, maybe they'll sell it to a glass recycler and it'll be turned into fiberglass or some kind of glass bottles, or more often it's filler in some kind of other process. It's very hard to reuse this, and a lot of manufacturing processes are very demanding. You can't recycle mixed content without just destroying the quality of the final product. Plastics is another example. It's like, yeah, you're going to reuse some plastic bottles, but you've got, what, some residual pops and beer. Maybe somebody puts cigarette butts in those recyclables. DIA. They're going to keep it. I was visiting recently just to see if they had like fire sale signs. You know, I'm $50. I'll put $50 on that one. I'll take it home. And this is a contemporary of Tiffany's, and it's just, for me, it's the most beautiful piece in the DIA. And they got glass done with that process where they're mixing colors and swirling colors. And like Tiffany, what they'll do when they don't get quite the right color, they'll double layer it. So you've got, this is actually a three-dimensional piece because they've got like a large panel and then you've got a couple of smaller panels right on top sticking forward a quarter inch. So it's very impressive, the workmanship on that one. So if you're doing that kind of labeling stuff, don't use cast iron. I started with cast iron because I needed a bigger scoop and I already had the glass molten and ready to go, and damn it, I need to do it today. So I grabbed that and then I welded some stainless quarter-inch plate around it, and it was very instructional. The stainless is great, and the cast iron, it stays brittle because it's cast iron. And it was fine until I started flexing it, trying to squish it, because it's also too big for the door of the oven. That was one of the many FUBAR experiences that I had in understanding. This is the same Vulcan glass where I've done these swirly amber with silver amber colors, and after I've got a cool sheet, crack it, and lay the pieces out, and then fill those gaps with a nice red, and then refuse it up. And that'll get me the quarter-inch thick. It's easy to do quarter-inch thick glass with all kinds of color patterns because when glass sits in the furnace, it always pools up. That's just a function of surface tension versus gravity. Water will pool up maybe 1/8 of an inch thick when you just dump it on the table. No matter how much you, just a big pool or a small pool, it's always the same thickness because of that relationship between surface tension and gravity. Glass will be a quarter-inch thick, so if you want it thicker than that, you have to dam it into an area and let it build up. If you want it thinner than that, you've got to roll it out. You can actually go into your annealer with sort of a steel roller and just roll that thin, or grab it on the edges and pull it out a little bit if you're careful, and get down to 1/8 of an inch depth. That piece of churning glass color. If you don't have the massive furnaces and you want to mix some colors, just put them on a little kiln shelf, tilt it after it's molten. When it cools up on the bottom, you're actually going to have a nice little swirly bit of color there. That was a neat little trick I learned. Oh, what else? So we're going to back up and talk about what we're looking at behind that. That is a small oven for melting. And this was a metal heat treating oven I reconfigured for glass. Reconfigured because it was a 440 volt oven. This is a good time to talk about electric heating, and then we'll get into some fuel oxygen mixture changes. This was a 440 oven, but I don't have 440 in my shop. So what I did was take extra bits of nichrome wire, and I shorted out half of these. And it worked beautifully. So I'm pretty happy about that. When you're doing if you're making an oven from scratch, or if you bought like an old even heat and coils are junk, you want to redo it, you can do that fairly easily. We'll get into where to buy nichrome wire. You get it, and then you can wind these coils the same way. You probably haven't done chainmail, but the way you do either of these is you have your big spool of wire. You have like a 1/4 inch steel rod. You put it into a drill motor, and you connect your wire to one end. You just hit the trigger there, and it wraps the wire all the way down this. So you can get a nice fast wrap that way, and then you can cut some grooves into your fire brick, either the Dremel tool or a table saw if you want. And then you just stick it in there, and you pin it in there with extra bits of nichrome wire. You're not shorting out when you pin it into place because it's not touching any other metal, so there's nowhere for the current to go. You can use a gauge of like 14, 12 gauge. It's easier to wind by yourself. 20 gauge, you can even use 22 gauge. It won't last as long, but if you just got a 6-month project, 22 gauge will do the job just fine. And you're going to want a piece that's between 30 and 70 feet long. And after you coil it, that's only 10 feet long because it's all in coil. The direct length is 30 to 70 feet. And there are some fairly easy to calculate processes to determine amperage on that. but for your regular residential 220, that's the length you're going to use. This book I had to bring. This is Glass Notes, Harry Halem. It's mostly a composition of some of the senior members of the glass community for the last 50 years. And it has great chapters on calculating your amperage. It has chapters on calculating glass ingredients and on all the kiln and furnace building that we're going to talk about too. So I wanted to do a layer. L-E-H-R is the name of it. It's a continuous annealer where you put your hot glass in at one end. You've got a conveyor belt that slowly goes through and it comes out room temperature on the back end. All the big production houses have it. Pilkington has one that's like a 1/4 mile long. It's very impressive. And I had to build an addition to my shop to fit this thing. So to make it, I first welded up this frame. I've got lids with hinges on the back, and I've got wood rafters going all along the middle so that I can build a nice arched roof floor. It was a great plan until it came time to burn out, because I figured, okay, I'll just put mortar all that brick in place and they're going to burn out the middle. And it was a good plan, except that as I'm slowly burning out layer after layer of plywood, it's accumulating uncombusted vapors in the middle of this 22-foot long thing. And then I'm venting out, and 4 or 5 hours later I hear boom, and I go in, and that middle section, bricks everywhere. I say, God damn it! Very important safety note: good venting there, oxidizing fire when burning out like this. Safety is so important. So Pilkington. One of my heroes. Pilkington developed the float glass process. That's where you've got your molten glass spread out on a layer of molten tin, and it cools in that way. So you get a mirrored finish on the top and bottom, pieces of flat, perfectly flat glass as large as you want. This is a little over 100-year-old process. He made like 1 million tons of scrap glass in the process of figuring out his process. It's something ridiculously huge. Can't quite remember the number. But I tried this at home too, because I just wanted to be able to learn to do everything. And the first time I heated up the tin bath, the tin oxidized. It turned into this nasty white crud. And I said, well, yeah, that's what liquid metals do when you sit for hours in an oxidizing atmosphere. And looking through the literature, I found out they don't quite use inner atmosphere of argon. They use a hydrogen-nitrogen mix. And that was a pretty neat thing to learn. The extra hydrogen at high temperature, it will attack any oxygen. It'll form some water vapor or it'll clean the atmosphere so that you can save a lot of money and have it mostly nitrogen that way. Very important savings when you've got this float bed that is that long. Before Pilkington, they were doing some agonizingly laborious processes for making flat glass. This is from CMOG, and it's a nice model of how the shops used to be. Here they're making small vases in a production capacity, but in a similar process, they'll make flat glass, and they'll make a bubble of glass that's really huge, and they'll have a hole in the ground, and they'll blow it and drop and blow and drop, and have a 2-story tall glass cylinder. And they'll wait till it's solid, and then they'll cut it around the top and cut it at the bottom, and they'll anneal it as a cylinder, and then they'll take it out, cut it into half cylinders, put it back in the oven, slowly bring it up to temperature, let it fall flat. And that's how they made large sheets of flat glass before the Pilkington process came around. Long before then, you might know the medieval process where they won't do a blown glass bubble. They'll just take a wad of glass and spin it into sort of a disc, and then you've got tons of discs. You can cut off on that disc into pieces for your leaded glass. These are some samples of cast glass. Casting is another way to go. For the cast glass process, you can use a lost wax. It's a popular way. So for these guys, what they would have done, like that neat dragon on the far left there, they would make a wax dragon or make a plastic or any kind of original, make a rubber mold, and then cast a wax duplicate. And then they're going to make sort of a cylinder of plaster flint mix around that. Burn that out, and then they'll put glass. You can even load your chunks of glass on top of this plaster cylinder, put it in the oven for days, let that glass melt down into place, and cool slowly, annealing in the process. And after it's cold, you kind of chisel out gently and carefully all that refractory around it, and you've got a neat dragon. The dragon will always have a rough matte surface on it, so then you got to do a lot of polishing if you want to get it to a smooth surface again. There are other tricks that we can deal with to get some glossy surface, but there are compromises there too, because that dragon is not going to have glossy surface in the crevices. It's not as nice. If you were to do that with blown glass, everything will be a beautifully smooth surface because it's all globular, organic smooth surface anyway, because it's liquid surface tension that you're working with. But for cast glass, you can go and fire polish it after you've demolded it and maybe sandblasted it, slowly heat it back up to temperature, take an oxyacetylene torch and just blast that surface really fast, and it will smooth it off. You can lose detail when you do that, but it'll be really nice and smooth. There are some processes where you can like mix. If you've got some idea of what you want to do with blown glass, but maybe you want to do a large series of it, or just something you can't easily do, you can cast some glass, clean it off, reheat it, and then after you've got a bubble, connect it to your bubble and do some work that way. Or reverse the process where you've got your blown glass piece, you can attach it hot to some sand cast stuff. You can also do some stamped processes. I brought somebody's sample where they take a hot piece of glass and they take a piece of formed metal. They wanted to just put their logo in it. And that's a great idea, a simple way to just blast some detail into some molten glass. And you get a fully smooth surface, no cleanup, pretty fast. But there are the limitations of what can be done with metal. We've got some coming up. This is another piece of cast glass at CMOG. That was a life-size woman's dress. It was a neat concept that they'd done. The annealing time on that thing would be weeks and weeks. Halfway to what they do. When Bob was talking about the NASA stuff, I was mindful that, you know, all those big telescopes that they use in NASA, those lenses that are the size of this room, they're like a yard thick, they will take years to anneal because glass is an insulator and you still can't have that temperature differential more than a couple of degrees from the center of it to the outside. So it's god-awful to do that. People are very patient. So the metal, here's a beautiful period sample. Center bottom is a stamp where they would just mash that into plate glass to get their logo. And these two, I'm glad they left the wooden model for what they want their bottles to look like, because they do a blown glass bubble, drop it into there, and blow it out and get that in detail. It's all going to be a little bit rounded, but it'll be great production quality, pretty cheap to do. And they did this for all kinds of drinking of vessels until they developed some of the bottle processes. I didn't bring a picture of the bottle process, but they've got these, you know, multi-million-dollar machines with thousands of moving parts, where just automatically they'll drop gobs of glass, clip them off into a little fixture, puts a little bubble in here, flips it over, blows the bubble up, flips it back over, blows it another time, flips it over again, and puts it in this annealer, and that's how all the beer bottles are made, and why they're so cheap. They're pennies a piece at this point because you've got sand and a production process. This is the older way to do it, the hard way. Venetian glass at CMOG, gorgeous done, where they've used soda lime glass. They could have done the same with borosilicate. For the bottoms, doing those bubbles on top would be a little harder to do. Borosilicate's pretty stiff and requires a higher working temperature. What else can I say about this stuff? Nothing. Let's go. Here, think this is a Steuben piece, which is a contemporary of Tiffany. I think he was on his team for a while too. It's a beautiful example of lusters done on glass. These are some magical surface qualities. You've got a little gold in there. They've got, sometimes they're reducing things. So they'll start with some special colored opals with metallics, put in a reducing atmosphere, and then they're treating it with iridizing agents that'll hit some of these areas in different ways from the others. The Jack in the Pulpit vase at the DA is another fine example. That's gold orine, which is, they call that luster that they've done. Beautiful stuff. For my own stuff, I've got out in the lobby some kind of a fake opal quality where I've got some brilliant little flecks of light in there, some internally lit rocks with fossils on the outside, and this kind of stuff on the top. So I was pretty happy with that. Dichroic. Dichroic is like all the rage. You cannot go to an art show without seeing dichroic jewelry anymore. I don't even see any of the audience. Kevin, you should have brought a nice dichroic earrings. Yeah. So dichroic is gorgeous stuff. It's really intense colors. You've got multiple layers of metal that are deposited with the plasma. It's not the same as an iridized process. It's hard to do. You can actually take your piece and send it out to CBS Dichroic, and for a stiff price, they will put a dichroic surface on it for you, which is pretty neat. You can do it yourself. Marshall had some very clear ideas on the details. You can basically take a vacuum chamber and a TIG welder and do your own dichroic. You want to have a target where you're vaporizing some titanium, even iron, variety. There's like a dozen different metals that they use in many layers to get some of it, because they've got dozens of different qualities: green, blue, magenta, cyan, a lot of stuff. And some are done. This is a beautiful example that one of the students had done, and just taking clear, transparent glass with dichroic surface and assembling it with this very modernist looking piece of art. 400 degrees, I think, is the ambient temperature you want in your vacuum chamber if you're going to do your own dichroic. You won't need a lot of metal to do it because the surfaces are so thin. So this is, moving on, a pedestal for a day tank. A day tank is a furnace, called that because this is as much glass as you want to use up in a day's work. I went overkill on the base for this. This cost me some. That's probably 450 pounds of steel. I wanted no flexure on this thing. Overkill. This is the top side, and a lot of folks in glass do make their own day tanks and other equipment. I learned that you don't actually have to mortar the stuff. Here we're just putting layers of brick in, and we're clamping it with threaded rod all around the side and squeezing it in place. It's a sufficient process, and it's easy to rebuild. Because if you're using the flooring whites or other things, eventually you're going to want to replace your innards. So you don't have to throw the entire thing away. You can save all the outside brick and just reassemble it, and you're only replacing the liner brick on the inside, which is a hard brick. It's important to segregate the kind of brick you're using. What we're seeing in the top center, the roof, it could have just been fire brick, but because I'm using nuggets of glass and I'm just shoveling coal nuggets in on top of the molten nuggets, you'll get some that explode. And because the whole inside is hot, it's going to stick to the roof of it here and there. And glass will etch into fire brick and corrode it a little bit. This stuff is a lot better for resistant to it. But it's not a good insulator. The lower temperature fire brick is the best insulator, and ceramic wool is the best insulator of all. You can't really build the walls of the thing with it. You can just lay it on the roof, or some people use just that. So they'll take a steel drum, they'll just throw in a whole bunch of ceramic wool, and now they've got a glory hole. It's pretty cheap and easy to do something like that. Yeah, 450-pound steel pedestal. I foolishly tried to lift it, and I got myself a gruesome hematoma in the arm.
Wait, that's not glass?
That's my arm.
What's your arm look like now? Okay.
I'm good.
Okay.
You scared the shit out of me.
Yeah.
Getting old, no excuse for that. All right, that's how it got done. I'm using my right hand here because my left one was still pretty messed up at this time. Measuring my temperature. That is an infrared temperature sensor. I love that thing. That's about $100, ordered from eBay from China. Granger has them for twice the price, but they're a little bit nicer if you want to throw some money at that. The door of this, I've got some fire brick and then some of that ceramic wool on top. And at the very top, you can see the end of a pneumatic cylinder. Put up a cheap pneumatic cylinder with a foot pedal, so it's an air-powered door. Some people have it slide sideways, some want to come and open this way. Some people put a little hole in the middle and have a double door so that it can do glass blowing and have the batch at the same time. It certainly saves on fuel costs if it can do both at the same time. So how are you getting fuel into your furnaces? I'm using propane. A lot of people use natural gas. I only learned recently it's not an arbitrary choice. Natural gas costs less than half as much as propane does. So for God's sake, if you get natural gas to run your glass equipment, do it that way. I'm not on city infrastructure, so I got to use propane. So that's one of the reasons I use cullet instead of batch. And I forgot to mention this before. When you're making your own glass, yeah, you can save on buying cullet by going 50 cents a pound for glass batch from spruce pine, but it absorbs a lot of calories when you're converting that into a uniform glass. So it's like twice as much fuel cost versus just buying the glass that's already fused up into that state. So when you're making your furnace, you've got a squirrel cage blower on the right side, and you've got your fuel coming in, and then you've got a burner. You actually don't need anything more than a simple pipe going right in there. You've got a little pipe coming in with your fuel, and then a larger one where your air is coming in. And if you want, you can put a little thruster, and that makes it a little more uniform combustion. But ultimately, all the calories that you're putting into there are turning into heat. So it's going to be combusted in there one way or the other. This is helpful. Good combustion is helpful for when you've got a cold oven and you're starting it up. Flame is liable to go out if it's not mixed properly. The critical part is the fuel-air mixture, because we're working with propane or natural gas and air. There's only so hot you can get. You can get your 2400 Fahrenheit, but you're not going to get much more than that, and it's going to take a while to build up. And if your air mixture is off, you're not going to, it's going to drop quickly. You'll be running overnight and come out and see that it's barely hot. It's like 1900 Fahrenheit, and you're still wasting all that money on fuel, but either you've got too much air in there, which is to get the right thing. So another way to save money is using a recuperator, and this is a doomed recuperator that was too small. This is all stainless steel. It's corroded so much I can't even get air through it, but I had to save it as a beautiful example. The theory is that hot air coming out of your furnace is waste heat. If you can pass it through your fresh air and transfer the heat to the fresh air, you're actually saving a lot of fuel costs. You can cut your fuel costs by 30% with a recuperator, and most of them, they're about this tall. You've got either ceramic tubes or some stainless tubes, and you've got the hot air on the outside of the tubes and your fresh air on the inside, because you don't want combusted air going right back in. You don't have the oxygen there for the combustion process. Recuperators are good for your long-term use. So this one is a drop oven. Corning also has one. They had one for a little while. I had some applications where I wanted to try where I'm not going in with a ladle or a gather. I wanted the glass to drop right out of the bottom of the oven. So I've got this special crucible made with a hole in it, and I've got this plunger. Plunger goes in, so when I want some glass, I just lift the plunger off, and glass drops right out the bottom there into the scoop that I had going. Then I'll add a secondary flame there just to keep that hole really hot, because otherwise, if I had that plunger down, it will freeze right around the edge of the plunger and won't be able to bring it back up. This is Corning's gathering. It's like the most ridiculously lavish, polished thing I had seen. You know, I'm so used to all these garage setups. They are the opposite. They throw a lot of money at these projects too. It's worth noting that Corning is funded by Dow Corning, which is producing the global fiber optic infrastructure. So they've got a lot of extra capital for these neat art projects. So they've also got a great library there, Rakow Research Library, and they had the original books from the Middle Ages. I can't read Middle German, but it was sure neat to see it. Glass recipes from that far back. They also had this. I'm looking through the contemporary art, saying, what is this? How did they do this? And I had to find out. And I'm just staring at this for a long time, and I read a little bit here and there. So what this guy did, that was a simple blue vase, and then he put some resist on the surface, and then he put it in some. It was either acid, hydrofluoric, or sandblasting. I forget which now, but you can do it either way. And they just add super deep into it, and then they'll electroplate copper on top. You start with electroless nickel, and then you can electroplate almost any metal you want. In this case, he did copper on it, and certainly he has some weird organic, novel processes going here. Kudos to that guy. They also had huge variety of the things that can be done with glass, and they had some neat optical effect stuff. So I just had to share one with you how they'll have partial mirrors, parabolic mirrors, reverse mirrors, good lighting. Everything like that. This guy, Chihuly, you probably heard of Dale Chihuly, world famous glass guy. Got the eye patch going. They didn't use that in the glass shop. I think it was a car accident or something. And then he's got a team, so he just kind of stands around. And he was at the Toledo glass place. And the comments I heard was that he basically brought some women to dance around while the gaffers were making the art, and he just kind of stood there looking good. And he'll have he had these posters with pastel colors, and he'll instruct his team on what to do. So he'll just swath some color down and say, "Do that," and then they basically go to work turning that into his vision, and it was surreal. He, as it turns out, is not the multimillionaire you'd think he is for all that. He was instructive that when he was starting his career, and learned this from one of his students, he got investment capital, and he signed in blood for that investment capital. And he sold a couple years ago a couple of chandeliers to some Sao Paulo or Rio casinos for $500,000 a piece. And 90% of the profits of that go to those initial investors, And then he's paying out his team of very talented young people. He's got enough left to live comfortably, but he's not going to be flying around the world in this private jet.
They're in the Bahamas and
well,
at the Atlantis Resort.
Was that so? Okay.
Yeah, I saw them there. They're beautiful.
So there are dozens of people doing similar chandeliers now. His name is worth a lot. And he's earned that. He was the first guy. He was the pioneer. But now, everybody's got that. This picture is one of his students, one of his team, that's a Chihuly as far as I can tell. And I went and looked at his other stuff. It's gorgeous glass. He was an angry man because, it doesn't matter if you can do the same thing. If you're 20 years too late, you're just a fish in the pond at this point. Yeah. I hope he's doing well. It's good stuff, but man, it's an uphill struggle. All right, and this is my uphill struggle. This is Urania. That's a life-size bronze and glass statue. And I talked about things you can do with stained glass. Some of these stained glass pieces, and this is a sample of that silvery blue that I had done, where you get pretty much clear pattern blue this way, and you get nice silver patterns from the front. Yeah. So I took these things, and I've got this life-size sculpture, and where I wanted glass, I'm making some plaster molds, and I'm putting the glass down and those into the slumping oven, melting it to the shape, pieces about a foot tall. Then I'll do the reducing process. I'll quickly bring it out of the oven, take oxypropane, because you gotta have that super hot flame or you won't get the right reduction. Good reduction has to be pretty fast and very strong, hot, and reducing flame. I'd even tried making a annealer where I've just got a nozzle and I'm putting fuel air to put a reducing atmosphere into the annealer, but it was going too slow, raising up the temperature, so I couldn't get it. I had to bring it out, use oxypropane to get that reduction. So all those pieces are then cold set into a framework, a lattice, to get those things. And this is the inside of the piece. So I've got sort of a LED floodlight and then fiber optic cable just coursing throughout. And it was a sort of a constellation starry pattern I got to achieve there, because as you work around the piece, you're seeing these slowly changing configurations of light pattern, and it really, really came out nicely. I was pretty happy with that one. Another sample of some mixed media. This is a lamp done with a bronze stem, so I'm casting a lot of bronze. Afterward, I've got these holes set in, so I'll put some nice, this homemade stained glass into the column. I've got a string of LED lights on the inside, and the top I've got some whites, ambers mixed, and then that silver blue pattern, and then some purples and some ambers around there. I was pretty happy with the way that turned out too. Too expensive though. These were retailing for like $2,000 to $3,000, and it's like, there's not a lot of folks with that kind of capital. You can go to Home Depot and buy a nice Tiffany replica lamp for like $80 now. China is an issue. It's good for the Chinese workers to be able to do that, but it's not so good for us. Which way am I going? Here we are. All right, suppliers. So if you're doing your own stuff, you're going to know where to get your materials from. And these are some very handy names to know. Auber is where I'm getting controllers for the kilns. You can get a programmable temperature controller for about $100 from Auber. That's necessary for glass, because your annealer, you're going to want to ramp very slowly through that strain phase, faster through the rest of the cooling, and you want to be able to hold the temperature, so programmable is essential. They also got some nice cheap temperature controllers, solenoids and relays, and some temperature probes as well that you can get to monitor your temperature. Roven Ceramics is where you're getting all the base ingredients for glass. Thank you. And your sand, your sodium hydroxide, a lot of the metal pigments that you use to color your own glass. We're almost done. This is the last string here. Fire Nation is in Toledo, next to the Toledo Glass Pavilion by about half an hour west of there. They've got their distributor, a stocking distributor, so you can go there and get a pallet of nuggets. You can get the Libido formula, the Spectrum Premium are there also. I go there a lot. K Industrial is local, that's in Livonia. So when you're building your annealers, they've got fire brick, they've got the inside liner brick that you'd want, they've got some mortar, and they've got various grades of ceramic wool. So that's the place to go in Livonia for that stuff. HIS Glassworks is for cold working. They've got the big diamond pedestals. I got a smaller one for about $400. There's no way around it. Those things are expensive, and they're really hunted for alternatives, but I couldn't find them. So McMaster Card, that's where you get your nichrome wire and various fixtures and tools. They've got a bazillion things like Granger, but their website is better organized by topic, so that's where to shop for a lot of stuff. Granger has some better blower motors, your squirrel cages. If you're a real cheap bastard, you can use a shop vac as your blower. They're just loud. That's the only down to there. You can also use a vacuum cleaner if you wanted to. Even a hairdryer will do the job for a small furnace. And Joppa Glassworks, they will sell some of the nice burners and safety equipment. Yes, ultimately safety needed to be mentioned. I'm a terrible example. Don't follow my example, even though I still have all 10 fingers. I killed myself despite coming close a couple of times. I think that's everything. That is everything. I want to thank you all for coming today.